Hello everyone, I am Takuya Furuta, a researcher in Japan Atomic Energy Agency and a member of the developing team of Monte Carlo simulation called PHITS. First of all, I thank the organizers for their great effort to have the international conference at this difficult situation. And also, I thank the organizers for giving me this nice opportunity to talk in this interesting session. The title of my talk is Performance of Voxel and Mesh Phantoms in PHITS. These are outline of my talk. Firstly, I will explain what is PHITS. PHITS is the abbreviation of Particle and Heavy Ion Transport Code System, which is the general-purpose Monte Carlo simulation code. PHITS can transport almost all the particles, including neutron, proton, electron, photon, and heavy ions, with wide energy range. PHITS is provided in all-in-one package, including source files, binary data, data libraries, and so on. Now PHITS is available in free of charge by submitting application form via PHITS website. PHITS has been applied in many research fields, including accelerator designing, radiation therapy and protection, radiation studies in space and geoscience. Today, I will explain the performance of voxel and mesh phantoms using this code PHITS. Background. Conventionally, PHITS adopted very simple geometry, which is combination of simple surface, such as sphere, box, cylinder, and so on. So it was difficult to construct complex geometry. On the other hand, the polygon mesh geometry, which is often adopted in computer graphics, is suitable to describe fine and complex geometry. In fact, there is a trend. Human phantom representation is shifted to mesh representation from the conventional voxel representation. The polygon mesh geometry is already adopted in other Monte Carlo simulation code, such as MCNP and GANT4, although there is a remaining computational problem. Therefore, we decided to solve this problem and implement a function to treat mesh geometry in PHITS. Let me explain the computational problem of polygon mesh geometry in Monte Carlo simulation course. Surface search process is required in particle transport calculation. When the particle is located at this position, we need to find the next crossing surface from all the surfaces enclosing the region. For the polygon mesh geometry, normally each region is composed of many surfaces, which requires many surface search processes. When the number of mesh increased by complication of the object, number of surface search increases. This means computationally explode for fine mesh geometry. Because of this reason, mesh phantom requires more computational time compared to voxel phantom in Monte Carlo simulation codes. To solve this problem, we decided to limit the compatible mesh geometry only to tetrahedral mesh in PHITS. Tetrahedral mesh geometry is a geometry composed by aligned tetrahedrons. number of surface search required for tetrahedron is only 4. Therefore, this makes the algorithm to be simple and faster the computational time. Implementation of tetrahedral mesh geometry in PHITS. Even we decided to implement tetrahedral mesh geometry, there is one remaining problem. The problem appears when a particle comes into the tetrahedral mesh geometry from outside, like this. In this case, search among all the surface of the object facing outside is required. This means number of surface search increased as number of meshes. Thus, the previous problem was not solved for this situation and becomes bottleneck of computational time. We therefore introduced a computational acceleration algorithm. We created space subdivision map at the beginning of calculation in the following way. First of all, we consider a box which can accommodate the tetrahedral mesh geometry inside, and divide the box into half for x, y, z direction, totally 8 regions, and count the number of outer surface at each region. If the number of surface exceeds the defined parameter, we subdivide the region again. We continue this process until all the regions satisfy the condition that number of surface is less than the parameter. The subdivision map is decoded, and at the stage of transport, we only refer to surface inside division at the location. In this way, the number of surface search at each region is limited to the parameter at maximum, and therefore the bottleneck problem is solved. Without this algorithm, the computational time exponentially increased as the increase of number of mesh. On the other hand, with this algorithm, we confirm the increase of the computational time was suppressed till proportional to number of mesh in one dimension. We conducted several benchmark tests using the newly introduced tetrahedral mesh function in PHITS. Firstly, we compare the computational time between Voxel and tetrahedral mesh. The computational cost for transport in Voxel is supposed to be minimum because of its simplest representation. So by this benchmark test, we can judge how good is the computational cost for transport calculation in tetrahedral mesh. We define the same geometry by dividing the cubic water phantom in this way and check the computation time by varying the mesh size. Firstly, we confirm reasonable agreement of obtained dose distribution between voxel and mesh representation. The measured computational time for each mesh size is shown in this figure. Since the number of mesh is different between voxel and tetrahedral mesh, we sorted by result of number of boundary crossing in this figure, which should be proportional to number of meshes in 1D. This is the result for protons, and this is the result for photons. Triangular symbols indicate the result of a tetrahedral mesh, and square symbols indicate the result of voxels. As you can see, the computational time for tetrahedral mesh is almost equal to voxels. This means the computational cost for each boundary crossing for tetrahedral mesh is as small as voxel mesh, which is supposed to be one of the best. In the previous slide, I explained the computational cost for tetrahedral mesh is as good as voxel mesh. But there is an advantage for tetrahedral mesh. That is, the complex geometries can be constructed with less number of meshes by combining different size and shape of tetrahedrons. This is the example of computational human phantom. For voxel mesh, the size of the voxel is defined to represent the smallest structure inside the phantom. Therefore, large number of meshes is required for voxel mesh to represent macroscopic objects like human phantom. On the other hand, for tetrahedral mesh, we can choose smaller mesh for smaller structure and larger mesh for larger structure. As a result, we can represent dosimetric equivalent phantom with much smaller number of meshes using tetrahedral mesh. This also affects the computational time. The computational time for tetrahedral mesh becomes less than voxel due to less number of meshes. For this case, the computation time for tetrahedral mesh is almost 1/4. We also compare the computation time between different Monte Carlo simulation codes. We use different complexity phantom to compare. One is coarse mesh, which is tetrahedral mesh phantom shown in previous page, and the other is fine mesh, which is the ICRP mesh phantom. This is a work done by my Korean colleagues of Hanyang University. Firstly, we confirmed convergence within statistical uncertainty among different codes. This figure shows comparison of the computation time for photon irradiation and neutron irradiation. Simple comparison is difficult due to difference in codes such as cutoff parameter, but it is still possible to compare the variation with different phantoms. As you can see, PHITS algorithm successfully suppressed the increase of computation time for finer mesh phantoms compared to other Monte Carlo codes. Other detailed comparison between Monte Carlo simulation codes is also shown in this paper as well. Summary. Particle transport calculation in tetrahedral mesh geometry becomes possible in PHITS. Our results shows the tetrahedral mesh representation can reduce the computation time as well as better description of complex and fine geometries. Future plan. The paper by Dr. Han also shows the performance of multithreading parallelization. Unfortunately, we found the speedup factor for large number multithreading calculation of PHITS was not as good as others. We are currently working to improve this performance. That's all my presentation. Thank you for watching my presentation.